So this is a report on the Decision Support for Data Segmentation, or DS2 project. It was one of the sub-projects of SHARPS that was mainly occupying the last 2 years of the project and has not been reported out very much yet. So I'm pleased to take this opportunity to start telling some things about it. One of the things that one is struck by here is how many of the problems with security and privacy are at least partially solved by poor interoperability and poor communication capabilities. And so in particular, the fact that the records were piled in a filing cabinet down in the basement, provided a certain level of security guarantee for people. So segmentation is the ability to break the record up into pieces, and to some extent it was achieved by the fragmentation and poor communication in the industry. So for example, you might have your immunization records with your primary care physician and your substance abuse treatment with the substance abuse treatment facility, and neither of those parties needed to know about each other. And if you wanted to share those records with someone, then if you're in either institution, they can go down to the basement to the filing cabinet and find out about you, that is, anybody at that institution. If you're at a different institution, then the only way to do it, or the most common way, would be to fax the thing. And so what you have to do is to prod your physician to please send the records to this other party, and then once they've done that, then you can go and have your appointment with the other party. And this had the interesting side effect of security was helped by this, because obviously the patient approves of something he has to prod somebody to do. And moreover, when the physician sends the record, they have at that point an opportunity to perhaps to take out the more embarrassing bits that they don't want to tell to the other physician, or whatever it is they want to do in order to protect the patient's privacy. Okay, so this is called push digital records. So the healthcare industry is heavily based on push mechanisms. I send you something. Think of email as the classic push kind of technology. So as we move, though, from the emergency, the EMRs, the electronic medical records, which is just the idea that you have a proprietary digital format for the data, to EHRs, which is the idea that they have some interoperability so they can be transmitted, then it offers a nice solution in this space to continue with the push model. And so what you do is you treat it kind of like email. And so I was pleased that the previous speaker helped tee up a lot of the kind of things I'll be talking about here too, because InHIN Direct is the major program in this area, which is a kind of email-like, secure email-like system intended to do pushing of the medical records. On the other hand, this has some significant disadvantages along with fax. It's slow for some applications, like you can't write a letter to have someone send something to an emergency room. It assumes the originator knows what the consumer wants. If the patient is meeting with somebody else, then if they're going to send something, and they're going to send, say, only a part of the record, then you assume that they would know what the recipient wants. It also assumes that the originator understands privacy expectations of the patients, which might well not be true at all, and so that what they send might not depend very well on the patient consents or wishes. Now, an alternative model that has been enabled by interoperable health records is pulling digital records. And for computer scientists, this seems like a very natural paradigm. It's scary to the medical profession, but very normal to most people. It's what you do with a web browser. You go and you search for data, and then you pull the data to yourself based on your search. So it's like doing queries, and it addresses many of those problems. There's no need for the patient to prod the physician to send the records, usually like with a fax or now with the secure email. The consuming provider can participate in determining what's needed. Okay, that is, they can query for something, and if they don't find what they need, they can make another query. Okay, or the query that they make first might lead them to the query that they make second. can operate quickly at the point of care. So like if I need to know your allergies, then in the emergency room, I can pull that up in principle. Okay. And this approach has been explored by the state health information exchanges, like some of the ones we were discussing there in the architecture there. And it was also recommended by the PCAST Health Information Technology Report, the report to the President from the scientific advisories. And however, it has some challenges. There's some infrastructure requirements and there are threats to privacy. And so I wanted to get into these privacy concerns with the pull system. And so going back to that example before, if the system is a pull system and all the data is sitting out there in a kind of distributed database for people to pull it, then how does the pull system, regulate the access to the data? So you've made something so that it's really helpful. It can get you the data you need when you need it. You can get it immediately and so on. But now you've made the system too oiled. It's very quick to get the data to wherever you're going. And so, for example, does the pull system allow everyone to access both the primary provider record and the substance abuse provider record? Okay, and so you've got this very sensitive type of data hanging out there and this much less sensitive type of data, and the circumstances in which you need to have both are going to be pretty rare probably. Okay. Another thing is that the other one had a certain kind of manual part because the physician would review the record. The physician's sending the record, and so therefore there's some, kind of like if he's going to send it to somebody, he thinks about why he's sending it to somebody in particular. And so it kind of slows things down and assures that things go in accordance with somebody's wishes, okay? Whereas that manual push step is missing in the pull model. And the response also is never actually seen by any of the parties that are sending the data. So when you pull from, say, 5 parties, no single one of the 5 you pulled from knows what the assembled record that the recipient has looks like. And so the result is that none of the parties providing the data actually has a total view of what information is actually being shared. Okay, so these concerns have been met by standards for the metadata, and extra sensitive data and standards with privacy patient consents. Now the DS2 project was to take a look at this scenario and look at a question beyond the current state of the art. So mostly the way this has been thought about is you have a list of the sensitive terms, and if the sensitive terms come up, then the document has sensitive data, and then you would regulate its flow. And so the patient says, I don't want to share my HIV status. Then what you do is you search for HIV terms, and if you see any of those terms, you say that this has that data in it. However, a problem with this is that there are inferences that you can make from context, particularly for many of these things. It's not that there's a single thing. In the case of HIV, you might have just the flag that says this patient has HIV. But if you remove that flag, most physicians can still easily tell whether the person has HIV from the rest of the record. Okay, and so the context of all the things together determines a lot about what's knowable from this. And so the DS2 project is looking at a way of reasoning about the inferential integrity of these records at a general level. Okay, so I wanted to show you a little bit of the technology associated with that. The idea is to divide the thing up into 3 parts, and the first is a predicate. So for example, let's take the HIV case. If you want to know whether someone has HIV, a predicate will say this medical record has evidence that the patient has HIV in it. So that's a yes or no. The reducer is the security function of removing that data so that it is not available in that record. This is shocking to some people, particularly physicians. I don't consider it very shocking. As a security researcher, it's least privilege. Basically what you do is you break the record up into pieces. If you need to know about the HIV status, you can ask, but it isn't included by default. And so perhaps the record is coming in pieces and you acquire for the pieces you feel you need and you don't ask for the pieces you don't think you need. And then finally, a safety checker, which is if you didn't have the complete record and you did actually do something like prescribe a medication, then it might warn you that some of the parts of the record you didn't look at are relevant, and so you better think twice. Okay, so there's a safety checker. In effect, safety checkers are done now by consolidation at pharmacies, because you'll have multiple providers making prescriptions where none of them are fully aware of the full medication list, and then the pharmacy tries to assemble that. So the project here works in the following way. This was our primary concept, which was to view access control in the medical space when we're talking about this segmentation problem as a form of clinical decision support, rather than, you think of like access controls like role-based access control. You have an access control matrix and this sort of thing. Whereas in this space, a lot of what you need is something more like clinical decision procedures. Does this look like this implies HIV? And so if it looks like it implies HIV, then maybe it needs to be segmented if there's a concern. Okay. So this is warning me I had to get my talk finished. Okay, so the way that the system we built works is that it takes in a standardized format. I talked about this morning, these standardized formats, the CCD, or continuing care document, pulls it into a system that converts it to a virtual medical record, or VMR, which is a medical record that has been optimized for clinical decision support computation. And then it tags that with respect to the clinical decision information it feels is relevant to security and privacy. So we have a tool that you can go and play with if you'd like, which is called the Inference Analyzer. And what you see here is it has, in red, HIV has been deleted. And then what it does is it predicts, based on what's left, how likely it is that the person is an HIV patient, living with HIV. So this one, based on the rest of the record, it's 85% chance. And then if you go and you redact this, what'll happen is that 85% will drop. And then it has a little tab down at the bottom that shows you how you're impacting the usability of the record by removing parts of it. So if you want to break it up into sensitivity levels, where HIV is one sensitivity level, then it gives you some idea of like how hard you'd have to work to do that, and what you would lose if you did it. Okay, and so that's what that thing does. So here's an example of a case study where we used the underlying mechanism, that is the decision support system. So like I said, the common view of this is that you take a list of the terms that say have to do with mental health. And if you see any of those mental health terms, you conclude that there's mental health discussion in this document. But you might have combinations of terms that lead you to believe that certain things are true without it being the case that the individual terms would necessarily do that. In the case of HIV, combinations of conditions, you can see if you go to the analyzer and you try it out, you'll see that this is the case, will cause you to think that the patient has HIV positive even though it doesn't say so, okay? And so the way it does that, what we're doing here is using a machine learning algorithm, and we tried about 10 different kinds of these on different kinds of databases to do these inferences. And so this is an example of a ontology-based one, which uses a list of recognized HIV terms compared to a statistical analyzer that says if these conditions are present, it looks to me likely that there's HIV as well, like it's just been deleted, okay? And so we found that 78% of the records, the S is the simple reducer, which means it's just using the terms, and the P is the probabilistic reducer, meaning it's using, in this case, naive Bayes, which we actually found worked really well despite the fact that it's not supposed to, because the conditions that do the implications are not independent of one another. Okay. So 78% are unchanged by both. 7% changed the same way by both. In other words, they agreed on 7% when they made a change. So they're in agreement on 85%. And then 11% were more heavily redacted by the probabilistic one. And the idea there was it finds that certain conditions imply HIV without being on the list of literal HIV terms, okay? And so that there's an implication, an inference that you can make. And then another 4% were more heavily redacted by the simple reducer, meaning that they're official HIV terms, but from the probabilities, they didn't seem to make it any more likely that the patient had HIV based on the probabilistic inferences. Okay. Now, one of the things we did in this project was to look at applying this. We were particularly focusing on the Illinois Health Information Exchange. And so what you see here is the architecture we derived for that. The idea is here you have the local hospitals, and then they feed into this central system, which has the patient identity, the registries and so on for the patient records and for the patients themselves. And then you have a virtual repository. The states are very reluctant to actually keep the data. So what they do is they index data and then they pass it through the system, but they don't like to keep it in a repository because there's a concern that Americans frequently have that the government will know their health records. And so they don't want to keep them. And so then the system this is called as XDS is the standard, and then it comes over through here. You see the consistency checker and the consent manager. And the idea is that when the data flows through here and is consolidated, then these decision support systems look at it and say, if the patient didn't want to reveal his HIV status, do these records seem to do that? And then they will flag them as whether they do or not. So if you want to just use a predicate, it could say, look, this doesn't seem to be achieving the goals. This doesn't seem to be achieving the goals that the patient asked for in terms of it's a really lot of hints here. And so you would need to either like get the patient to give more consent or just say, look, we're not sharing records on this. Okay, so here conclusions and pointers. You see the timing is about there. It's a flexible and analyzable approach to data segmentation. I think there's a lot of claiming on the part of people that they can do this without, I think, a lot of proof or scientific, foundation. And so I think one wants to move to something more analyzable. And it's completed illustrative studies with HIV and pull architectures like the Illinois Exchange. And if you go to that site right there, you can find the inference analyzer under their demo, and it's kind of fun to try some different combinations of diseases. These are real patients, by the way, from the CDC database, and the inferences are from the CDC database. And so you can ask it to give you a random patient, and it'll pop up diseases that a random patient has, or you can ask for a patient with HIV, and it'll give you one of them. Okay, and then there are a couple of research reports on the project as well. All right, well, thank you for your attention.
Murat Kantarcıoğlu, University of Texas at Dallas. My question is, how do you compute utility of the remaining diseases, etc., when after reduction? So how do you know which disease is better for utility?
I think it's fundamentally a hard problem, but the inference analyzer actually does it in the following way, which is if you go to that inference analyzer thing to see how it impacts the utility, what will happen is you have a list of diagnoses, and then down below is a word cloud of conclusions that you could make. Okay, and so the word cloud has, hey, if the patient had these things, I think they might also have tuberculosis or whatever, okay? And then if you redact something, the word cloud changes. And so you can kind of see from the graphic, like if the word cloud just disappears, then you've eviscerated the the content. Whereas if you click it and it doesn't change, it means that based on the naive Bayes analytics that we had, it didn't much affect the quality of the data.
So there are a lot. There are a lot of people who are using this fragmented system to ensure privacy. And I've run into a lot of problems with that. So, for instance, there was a patient on lithium who wanted that information not included in her medical record. But lithium is a salt that interacts with a hell of a lot of drugs. And so by keeping that private, she may be killed by her other doctors who won't understand the drug-drug interaction.
Yeah, I should say from my experience with this, people are killed by these things. They go with the partial records and they get
Okay,
killed.
I take away the may be killed. The other thing is that I know of a hospital in New York where only the attendings can get to see the behavioral record. But because of that population, almost all of the patients have some behavioral records that are required, and thus the attending spends all of his time getting those records available to the residents who need to see them. And so this protection backfires to a terrible workflow clog.
Okay, that wasn't a question.